Okay, so we're going to talk about another graph. This time, we're going to determine the location of any intercepts, the intervals where the curve increases or decreasing, and the value of any extrema, and the intervals of concave up or down, and any inflection points to sketch the curve y equals x minus sine of 2x on the interval from 0 to 2 pi this time. So we don't need to determine a domain. We're not really interested in whether or not this function is going to be even or odd. And by the way, as far as intercepts are concerned, there's really only one intercept of concern to us, and that's what happens at x equals 0. We know that at x equals 0, y is equal to 0, so right away we actually have a point that we can plot right here. The question is going to be what's going to happen to the rest of the function. Well, one thing that we can actually point out is that in this function, where I have y equals x minus sine of 2x, we know that when we take a combination by addition of a function added or subtracted to one of these trigonometric functions, this first function will act as a center axis of the graph. If we were to go through and plot this, that means that on this graph, the line y equals x is going to act like a center line for this graph. Not only that, we note that the amplitude of the sine of 2x is 1. That means that this graph will never go any higher than 1 above that center axis. So we can just sort of mark lightly right here the top and the bottom of any amplitude for this function over the interval that we're interested in. So right away we actually have some information on a sine function without having to do too much work, and that's a nice thing. So what we're really interested in right here is what is going to happen when we look at our derivative and we look at our second derivative and we look for any points of increase and decrease. So this one's going to take us a little bit of work. So the first job, of course, is let's find our derivative. Our first derivative will be the function y prime is equal to 1 minus 2 cosine of 2x. And of course, we're interested in finding our extrema right here. That means our critical numbers are going to occur where y prime is equal to 0. Setting y prime equal to 0, 1 minus 2 cosine of 2x is equal to 0 wherever cosine of 2x itself would be equal to 1/2. Now remember that because this is a multiple angle kind of problem, what we're going to have to do is we're going to have to use our solutions for cosine of 2x equals 1/2 as follows. First of all, we'll note that 2x, the angle we're taking the cosine of, will equal either pi over 3, which is a first quadrant angle whose cosine would be 1/2, or 5 pi over 3, which is a fourth quadrant angle for which this function would be positive 1/2, plus any angle coterminal to it. And this is important. Remember, in multiple angles, we were using this general form to generate our specific answers, because look what happens now. If we actually solve for x by multiplying both sides by 1/2, we end up with pi over 6 or 5 pi over 6 plus any pi k values right here. And so to find the actual fixed solutions on the interval from 0 to 2 pi where that's going to happen, let's go ahead and substitute in for k. And if k is equal to 0, well, easily enough, we find pi over 6 would be such an angle, and that 5 pi over 6 would be such an angle. But then we have pi added to that, so 7 pi over 6 is another such angle. But so is 5 pi over 6 plus pi, which is 11 pi over 6. Right? And these occur when k is equal to 1. And all of these values are within the interval from 0 to 2 pi. So we're actually going to have 4 values right here. Now the next order of business would be to go ahead and let's substitute in values on the interval from 0 to 2 pi where these critical numbers occur. All right, here's pi just for reference, and I kind of reference myself right here. Here's pi over 6, approximately. 5 pi over 6. 7 pi over 6 and 11 pi over 6. And what we're interested in looking at is, are there going to be any sign changes over these intervals? And we'll note that to the left of pi over 6, if I were to substitute in 0, for example, into my derivative right here, I'm going to get a negative number. So it's going to be decreasing over a very small interval from 0 to pi over 6. From pi over 6 to 5 pi over 6, we'll note that the derivative is going to be positive, so we're going to be increasing on that interval. If I go from 5 pi over 6 to 7 pi over 6, we'll note that if we substitute in a value like pi, which is certainly in between them, we're going to get a negative value, which means we're going to be decreasing on that interval. From 7 pi over 6 to 11 pi over 6, I could substitute in 3 pi over 2, for example. I would find a positive value, which means we're going to be increasing on that interval. And then finally, from 11 pi over 6 to 2 pi, we're going to be decreasing once again. Okay, so we're going to be decreasing, then increasing, then decreasing, then increasing, then decreasing. So we actually have a few intervals over which all of this is going to happen. Next point that we're going to have to take is what happens to the second derivative. So let's take a look at our second derivative. We get y equals positive, that's a positive, 4 sine 2x, and we set y double prime equal to 0 to find any critical numbers of the second derivative. For our critical numbers, we'll note that sine of 2x, wherever sine of 2x is equal to 0, we're going to get a solution. So what that implies for us is that 2x would be equal to numbers that are multiples of pi. And so wherever x is equal to some multiple of pi over 2, we're going to get a coordinate point where we're going to get a point of inflection. Or at least a 0 for our second derivative. We don't know if that's an inflection point yet. We do need to look over our interval from 0 to 2 pi. So if we look on the interval from 0 to 2 pi, we'll note that substituting in a value like pi over 4 into this expression is going to result in a positive value, meaning we're going to have a concave up shape here. Between pi over 2 and pi, substituting in a number like 3 pi over 4 is going to result in a negative, which is going to give us a concave down shape. Then going from pi to 3 pi over 2, we're going to get a positive again, which is going to give us a concave up shape. And then finally negative again, which is concave down over this interval. So now we actually have enough information to help us out. We are going to have to go through and find some y values that make this happen. So let's go through and plot. First of all, we're going to have to start at 0, 0. We also know that at x equals 2 pi, y is equal to 2 pi. So this graph will pass through the point 2 pi at that endpoint. All right, so those are our two endpoints. But we also have values at x equals pi over 6. X equals pi over 6 is a little bit less than a half. And at x equals pi over 6, substituting it into our function x minus sine of 2x, it is going to result in this value right here, pi over 6 and approximately negative 0.34. And that's where we're going to get a relative minimum right here. We go to our next point at 5 pi over 6. At 5 pi over 6, 5 pi over 6 is just a little bit shy of 3 right here. And at 5 pi over 6, we get about 3.48. So right about here, 5 pi over 6 results in a value of about 3.48. At 7 pi over 6, which is just slightly to the left of 4 right here, between 3 and 4, we're going to find a value of about 2.88. So right about here. 5 pi over 6, 7 pi over 6. That's a 7 pi over 6 right here. 7 pi over 6, we get about 2.88. Probably make a better 7 pi over 6 right here. Let me try that again. And then finally at 11 pi over 6, 11 pi over 6, we get about 6.63. That's a maximum point. If we're looking for absolute maximum minimums, by the way, our absolute minimum occurs here at pi over 6. Our absolute maximum occurs here at 11 pi over 6 on this interval. The others are relative maximums and relative minimums. Okay, keeping track of these numbers right here from the perspective of our first derivative, we have a function that is going to decrease on this small interval up to pi over 6. That's a d for decrease. We're going to have a function that's going to increase all the way up to 5 pi over 6. It will decrease briefly again between 5 pi over 6 and 7 pi over 6. Will increase again all the way up to 11 pi over 6, and then finally decrease for a little spell right over here. Looking at our second derivative tells us that this function is going to be all the way up to pi over 2 concave up. So pi over 2, about 1.57 or so. From pi over 2 to pi, so from right about here all the way up to just slightly to the right of 3 and some change, we're going to be concave down. We're going to have a point of inflection right here. We're going to have another point of inflection right here at pi over 2. By the way, we should take a look at those points. Pi over 2 is a point of inflection. As is the point pi right here. And finally, 3 pi over 2, right about here. 3 pi over 2, 3 pi over 2. We're going to have another location of a point of inflection right here. So our graph is going to go concave up again, and then finally concave down all the way to 2 pi. All right, so let's trace that. What is that going to look like? You notice on the shape from 0 to pi over 2, we're concave up. It's decreasing to pi over 6 and then increasing. From pi over 2 to 5 pi over 2, it will be increasing and concave down until it reaches its maximum, at which point it starts decreasing in a concave down manner until we get to pi, and then it starts decreasing in a concave up manner. Then it starts increasing in a concave up manner all the way up to 3 pi, and from 3 pi over 2 all the way up to 11 pi over 6, it's still increasing and concave down till that point where it becomes decreasing concave down. So there we go. This is a picture of what our graph should look like on this interval from 0 to 2 pi.